lecture I am starting with selection of motor power rating. Selection of motor power rating. Now to select the power rating of the motor, it is to be very careful about the selection of the proper rating of the motor, so that if the motor is driving such a load, that is the load power is higher than the motor rating, this operation may be stopped by the power modulator because of the overloading conditions. Okay, that is, motor power to be selected in such a way that the motor load operation is either reliable, that is, it is to be selected based on these two criteria, that is reliability and number two is economical. Okay, that is, if I select, then what to do? If I select the higher rating of the motor than the load, then how much higher rating you have to select? You have to select, or say, if the selected motor power rating is such that the motor is unutilized, then what will happen? Because of the large rating of the motor core diameter or the motor core size becomes higher, then core loss becomes high. Number two, the rotor, mass of the rotor becomes higher, then the friction windage loss will be high. As a result, the constant losses, when a motor is running, then these losses are very common. That are, one is the fixed losses. Fixed losses contains the core loss, another is friction windage loss, friction and windage loss. Okay. These two losses are the fixed losses, and another is variable loss. Variable losses or variable loss is copper loss. Okay. That depends on the how much load is coupled with the mechanical load coupled with the motor shaft. If the load is increasing, motor current will be increasing and the copper loss will be increasing. That is the I square R loss. Okay. It is I square R loss. Okay. Then for the selection of the motor power in such a way that the reliable operation as well as the selection is economical selection will be there. Okay. Now, when a motor is running, then fixed losses and variable losses are continuously occurring, but these two losses will appear as heat losses. Okay, say if there is a motor, this is the stator part of the motor and this is the rotor. This is the rotor. Okay. We say this is shaft where the load is connected or coupled, mechanical load is coupled. This is the shaft. Now, when mechanical load is continuously increasing, the heat will be increasing because of the different losses. Okay, core loss, friction windage loss is constant loss, but copper loss is continuously increasing. Then this heat will be dissipated from the conductors, okay, or developed by the motors. And after some time, when heat generated by the motor is less than the surroundings temperature, the temperature of the surroundings, then it will be entirely absorbed by the motor. Now, when continuously after a certain time, heat when heat generation will be more than the surroundings, then it will be dissipated from the body of the motor, okay, to the surroundings. Then up to which extent the more it will be dissipated, that is when heat generated by the motor will be equal to the heat dissipated by the motor, then the equilibrium condition occurs. That is, heat developed by the motor will be equals to the heat dissipated by the motor. Then equilibrium condition will be achieved. This defines the equilibrium state. Equilibrium state. Okay. Now, it is very much important to select the motor power rating. First, we have to derive a thermal model of the motor. Okay. Thermal model of motor for heating and cooling. Now you have to first derive this model. Then first we consider, say, P1, that is heat developed by the motor. Heat developed, that is in joule per second or watt. P2, heat dissipated. Also in joule per second or watt. Next is M, that is the mass of the active parts. Mass of the active parts of the motor. Of machine in kg. Next is S. S is the specific heat. Specific heat of the material from which the heat is dissipated. That is in joule per kg per degree centigrade. A, A is the area of the cooling surface from which it is dissipating. That is area of cooling surface in meter square. All units are in SI. Next is alpha. Alpha is the coefficient of heat transfer. Coefficient of heat transfer or specific heat dissipation. Specific heat dissipation in joule per second per meter square per degree centigrade. Okay. Now theta. Theta is the mean temperature rise. Mean temperature rise. That is in degree centigrade. Okay. Now, to derive the thermal model of the motor, we have to make some assumptions first. What are the assumptions? Assumptions. It is considered that the motor is running with a constant loss. Loss is not changing. That is also the motor load. Load on the motor shaft will not be changing. That is, motor is operating at a constant load. Okay. Because loss is nothing but a fraction of the load to be delivered by the motor. That is number A, loss or heat produced remains constant during the temperature rise. Okay. Number B, temperature of the ambient is constant. Okay. Because the heat is to be dissipated to the surroundings temperature. Okay. That is temperature of the cooling medium remains unaltered. Okay. And the last one, heat dissipation, heat dissipated, heat dissipated is directly proportional to the difference in temperature of the motor and cooling medium. Okay, these three are the assumptions to be considered. Then, considering a incremental heat, that is during considering an incremental heat is produced during an incremental time dt. Okay, during a time increment dt, let the machine temperature rise. Let the machine temperature rise is d theta. Okay, then heat develop. First one is heat develop. That is heat develop inside the machine. That is P1 into dt. Okay, and heat dissipated to the cooling medium. Heat dissipated is P2 dt. Okay. Now heat absorbed inside the machine. Heat absorbed is P1 dt minus P2 dt. Okay. That is, you can write M into S into d theta. Okay. Again, you can write the heat dissipation, that is P2 dt. Again, P2 dt you can write also theta, that is, what are the parameters? Theta, coefficient of heat transfer is alpha, and the cooling surface A. Okay, cooling surface A. That is theta alpha A. Right? Then we can write P1 dt minus theta alpha A equals to ms d theta. Sorry, theta alpha A dt is there. P2 into dt equals to ms d theta. That is ms d theta P1 minus theta alpha A dt. Okay, or ms d theta dt equals to P1 minus theta alpha A. Okay, now considering say ms is the thermal capacity of the machine. That is thermal capacity of machine. That can be considered as K1, a constant. This is a constant. And alpha into A is the heat dissipation constant. heat dissipation constant. That can be written as K2. Okay. Now we can write K1 d theta dt plus K2 theta equals to P1. Now divide the entire equation by K1. We get d theta dt plus K2 by K1 theta equals to P1 by K1. Okay. Now this is in the form of first order ordinary differential equation. Okay. This is first order ordinary differential equation. Now this equation has two solutions. Since the right hand side of the equation is not equal to 0, then one solution is, the first one is the transient solution. Transient solution from complementary function CF. And another solution is the steady state solution from particular integral Pi. Okay. Now come to the complementary function, that is by equating the right hand side of the equation equals to 0. d theta dt plus K2 by K1 theta equals to 0. Now we can write from this equation d theta by theta equals to minus K2 by K1 dt. Okay. Now taking integration on the both sides. This gives, first one is the natural logarithm ln theta equals to minus K2 by K1 t plus C. C is the integration constant. Okay. That is, theta becomes e to the power minus K2 by K1 t plus C. Or we can write e to the power minus K2 by K1 t into e to the power C. Now e to the power C is constant. Consider e to the power C equals to m. That is m e to the power minus K2 by K1 into t. That is m equals to e to the power C. Okay. Now in general, theta can be written as e to the power or m e to the power minus t by tau. That tau is a heating time constant. Okay. Heating time constant. That is K1 by K2. Now coming to the particular integral. Now I am writing this equation once again, that is d theta dt plus k2 by k1 theta equals to p1 by k1. Solution of particular integral. Okay. Now the previous one is the solution of the CF. This is CF. That is d theta dt plus k2 by k1 theta. K2 by k1 theta equals to p1 by k1. p1 by k1. That is, we can write d1 or d, that is the derivative term, d plus k2 by k1 theta equals to p1 by k1, or theta becomes p1 by k1 divided by d plus k2 by k1. Okay. Now putting d equals to 0, putting d equals to 0, theta will be k1 will be cancelled out, that is p1 by k2. Okay, which is equals to the theta SS, steady state value. This is the steady state value of the temperature. Then overall temperature rise, overall temperature rise of the machine can be written as theta equals to theta SS plus m e to the power minus t by tau. Okay. Now considering at t equals to 0, now you have to calculate the value of m from the initial conditions. What is the initial condition? At t equals to 0, at t equals to 0, let the initial temperature rise. Initial temperature rise is theta equals to theta 1. Okay. Then putting this value in case of theta, I am writing theta 1 equals to theta SS plus m, that is m equals to theta 1 minus theta SS. Okay. Now put this value. Then overall temperature rise becomes theta equals to theta SS plus theta 1 minus theta SS e to the power minus t by tau. Okay. Now simplifying this equation, that is theta equals to theta SS 1 minus e to the power minus t by tau plus theta 1 e to the power minus t by tau. Okay. Now let the initial temperature rise of the machine is starting from 0 degree. Okay. Considering theta 1 equals to 0 degree centigrade. That is, the initial temperature rise is starting from the ambient temperature. That defines theta equals to theta SS 1 minus e to the power minus t by tau. Now putting tau equals to the time constant, heating time constant. Then if I put t equals to tau, this defines theta becomes 0.632 theta SS. That is 63.2% of the steady state value. Okay. That is, from this we can say that when the machine temperature rises up to 63.2% of its final value, we can say that the steady state temperature is achieved. Okay. Now this all about the heating of the motor. In the next lecture we discussed about the cooling.